Imagine a library holding 1,000,000 books, where every single volume answers a different question. A classical computer like the one in your phone or laptop or car works exactly like a librarian reading one book at a time. It is fast and reliable, but cross-reference 5 specific books to find a single pattern, and the librarian will still take hours. A quantum computer flips the script by letting a virtual librarian read every book simultaneously. It spots the pattern instantly and hands you the answer before your coffee even cools. That is the real promise here, and it is not science fiction, it is hard physics. Quantum computing simply processes information using the rules of quantum mechanics. It relies on subatomic physics instead of traditional classical logic. Classical computers run on bits that are strictly 0 or 1. Picture a light switch flipping on or off. Your phone solves every problem by toggling trillions of those tiny switches. Quantum machines use qubits instead. A single qubit holds 0 and 1 at the same time through a trick called superposition. Picture a coin spinning on a table. It hovers in a blur of heads and tails until you slam it flat to measure it. Then it finally picks a side. 2 more quantum secrets supercharge these qubits. U-bits. Entanglement locks 2 qubits together, so checking one instantly reveals the state of the other across any distance. It is like reading one book versus knowing every page in the entire library at once. Imagine flipping through a stack of books where every single page references another at the exact same moment. That is exactly how quantum machines think. Quantum computers use interference to amplify the right answers while canceling out the wrong ones. They ride wave-like patterns that act just like noise-canceling headphones for your calculations. This does not give you a simple speed boost like a new CPU ever could. The machine actually operates on a completely different logic. It explores a massive space of possibilities all at once, instead of marching through them one by one. A classical computer simply cannot tackle that kind of parallel search efficiently. Leave the library analogy behind and focus on the real magic. Quantum computers harness bizarre subatomic rules to crack problems that would completely stump a regular machine. Quantum computers excel at searching enormous possibility spaces. They map the single best route through 1,000,000 cities. They figure out how a new molecule might bond. They crack encryption codes that take a supercomputer longer than the age of the universe. Regular computers are built for following step-by-step instructions. The honest answer is no. You will never run a quantum version of Chrome. These machines are specialized tools built like particle accelerators rather than pocket calculators. But in specific domains, the impact could be massive. Drug discovery and materials. Science lead the charge. Simulating molecular interactions at the quantum level is something classical computers barely manage. Quantum computers could simulate entire drug candidates before a single vial is mixed, slashing the 10 to 15-year drug development cycle. They will also completely transform optimization problems like supply chains, traffic routing, and financial portfolios. Problems that make classical computers struggle for days to find a decent answer will resolve in minutes. Cryptography faces the real danger here. A sufficiently powerful quantum computer could break RSA encryption using Shor's algorithm. That mathematical breakthrough threatens to strip the digital locks protecting your bank account. This reality forces governments and companies to scramble toward post-quantum cryptographic standards. They are racing to future-proof every secure connection on Earth. Quantum algorithms might eventually speed up specific machine learning training runs. The science remains largely theoretical, so do not expect a quantum AI chatbot anytime soon. Optimization is the clear winner for near-term quantum advantage. Your GPS app just needs to find the fastest route through a city. That is a classic optimization problem. Billions of possible routes exist while you just want the single best path. A classical computer tests routes one by one. It eliminates dead ends until it finally finds a solution. A quantum computer explores countless routes at once using superposition. It uses interference to cancel out the bad ones and surfaces the best path. Logistics takes this further. Teams route thousands of delivery trucks across a continent while minimizing fuel time and driver hours. Finance teams balance thousands of assets against dozens of risk factors in real time. Power grids shuffle electricity across networks where supply and demand shift every single second. Airlines rebook thousands of stranded passengers during storm delays in seconds instead of hours. These problems are already happening in the real world. D-Wave, using quantum annealing, and IBM have already applied quantum-inspired optimization to live logistics networks. The hardware is still young, but the applications are rock solid. You cannot program a quantum computer directly in Python. You have to use dedicated frameworks instead. Qiskit leads as IBM's most popular open-source SDK. You write Python code, then compile it into quantum circuits. Those circuits run on IBM's real hardware or simulators. Google built Cirq specifically for their superconducting qubit processors. Microsoft took a different path with Q, a dedicated quantum language built straight into the .NET ecosystem. Xanadu created Penny Lane to tackle quantum machine learning and differentiable programming head-on. Under the hood, you are wiring quantum circuits by chaining operations called gates. These gates manipulate qubits just like classical logic gates, but they work on superpositions instead. The real bottleneck is algorithm design, not syntax. You only have a handful of proven methods like Shor's, Grover's, QAOA, and VQE to work with. Figuring out where they actually belong is the hard part. IBM and Google both run machines packing over 1,000 qubits. They are noisy and highly error-prone right now. That is exactly what we call the NISQ era, or Noisy Intermediate Scale Quantum Era. DARPA just called for new quantum cooling proposals in January 2026 because helium-3 shortages are choking the industry. The agency knows that bottleneck is the real deal. China's Zhujiang photonic quantum computer just proved it can handle specific tasks faster than any classical machine. The milestone confirms quantum advantage is real. NIST is rolling out new post-quantum cryptography standards right now. Governments are already prepping for the day quantum machines finally crack our current encryption. We still have a long way to fault-tolerant quantum computing. The race is absolutely real, and progress is accelerating fast. The scientific and economic stakes are enormous. What exactly separates a classical bit from a qubit? A classical bit sticks to either 0 or 1. A qubit can hold both states at once until you measure it. Which real-world problem holds the strongest near-term quantum advantage? The answer is optimization. Optimization problems power things like logistics routing, financial portfolio management, or energy grid distribution. You are hunting for the single best path across billions of options. Classical machines choke on that math. Why does quantum computing threaten our current encryption standards? It turns digital locks into glass. Run Shor's algorithm on a powerful quantum machine and factor huge numbers exponentially faster than classical computers. That speed instantly breaks RSA and ECC encryption. Most of the internet suddenly loses its shields. If that made it click, subscribe. We break down the frontier of tech and AI every day.